Welcome to this mathematics series on sets, and I'm expecting at the end of this video you will be able to define a set. You'll be able to read, you should be able to read, write, and use set language and notation as they appear in mathematical statements. Also, you will be able to identify types of sets, carry out set operations, and also I'm expecting that you'll be able to draw and use Venn diagrams in solving real life situations. So what are sets? Now a set can be defined as a collection of objects according to a well-defined common element or property. Okay, say for example we are talking about a football club, right? So we're talking about football club. So if you talk about football club, let's take for example, you have a Manchester United. All right, Manchester United. All right. So in Manchester United, all right, players, Manchester United players, they are a set. So Manchester United players is a set. All right. So you can also have set of collection of books. You know, we have in everyday activities people admire and they are involved in certain arrangement and collection of objects. So you can have collection of tools in a carpentry shop. You can have arrangement of students names in school register in alphabetical order. You can have a set of desks. You can have a set of shoes. You can have a set of dresses, a set of cutleries. You can have a dining set. You know, you can have a set of say names starting with S, starting with letter S. Okay, so you can have all of that. So that is what we call set. So a clearly defined collection of things, objects or numbers constitutes a set. All right. So now if we talk about the elements of a set, or we have members of a set. For example, what are the elements of or members of Manchester United players? We can have somebody like Luke. I think we have Luke Shaw. We have Rashford. All right, all right. We have all right, Marcos. All right, all right. So all of these people, all of these, they are the elements of Manchester United. They are the members of Manchester United players. All right, but if you have someone like Tani Abraham that plays for Chelsea, all right, so this Tani Abraham is not a member. So Tani is not a member of Manchester United players. All right, so we can say Rashford R is a member of Manchester United player set. All right, so that is how we look at the elements and the members of a set. All right, so we can say, just like I said before, you know, if when an element x belongs to set A, we write it like that. So x does not belong to this, then we write it that way. That is how elements of a set is being written. That is the letter that you can use to denote the element of a set. All right, take for example, again, we have if x is the set of all prime numbers, and we know that prime numbers are numbers that are divisible by 1 and itself. All right, y1 is not part of prime numbers. So we have prime numbers like 2, we have 3, okay, we have 5, all right, and all that. So we have 7. So if X is the set of all prime numbers and P is 7, then we say P is a member of X. Okay, because if X is a set of prime numbers, or if we are giving A to be 6, all right, A can be divided by 2, 3, 6, and all that. So 6, which is A, does not belong to the set X. All right, it doesn't belong to set X. Don't forget, you always write a set with a capital letter, right? So A does not belong to the set X, while most elements are written with small letters, right? So the element of a set are enclosed within braces with that symbol. So if you say, what are the elements of set A? Okay, that's all are numbers from 1 to 10. So just do 1, 2, 3, 4, up to 10. Then you enclose it again with a brace. All right, so this is how to write, all the elements of a set. It's supposed to be enclosed in a within a brace. All right, so let us look at finite and infinite sets. Now, if members of a set have a definite number, like the days of the week, we term them as finite. Okay, so what do we mean? When we have days of the week, we know that days of the weeks are from Sunday, all right, to Monday, I mean to Saturday rather. Okay, so days of the week, Sunday to Saturday. So this is finite because you can count it. All right. Okay. When we have a set containing uh, the players of Manchester United. All right, so easily you can know those names, those number of players are there. You can write that. All right, all right. When you have that's finite. When you have a set of say the months in a year, so we have from January, all right, February up to December. So, all right, so all these are finite. They are just you can easily count them. Okay, so that's a finite. So, but infinite, when you have say uh, a number, let's say a set is all integers, right? All integers. So you can't stop counting. You know, can count, you can't stop counting. So these are called infinite, you know. So counting numbers, they are infinite. So you can have, if you have a set of all integers uh, that are even numbers, they are also infinite because you can't just stop counting the numbers that are you can count up to billions, trillions, finding all the numbers that are even number or probably odd number. So these are infinite sets, unending infinite sets. Okay, so let's look at the subsets, and supersets. All right, so we're looking at subsets and supersets. And we know that a subset are sets which are contained in another set. For example, if you have two sets A and B, so set A can be said to be subset of B if all elements of A are also contained in the element of B. All right, so say we are given a number a set A to be 0, 2, 4, 6, and 8, and we're giving B to be a set, don't forget the enclosing a brace, 2, 4, and 6. All right, so we can say that B is a subset of A. Why? These two, you can find it here. This 4 is also here. This 6 is also in A. So B, all right, so how do we have to write the denote subset? So D is a subset. We do like this. B is a subset of A. All right. So B is a subset of A. So now, if B is a subset of A, then A can be called superset of B. A can be called superset of B. All right. So A is a superset. You denote it like this. A is a superset of B. Why? Because everything in B, you can find it in A. So A is a superset of B, just like I say A, like A is a mother of B. All right. Why B, they are children of A. All right. So when you say B is a subset, it means B is a child of A. All right. So A is a superset, which is the mother of B. But B as a child cannot be superset of A. No, it can't be. All right. So that's it. Let's move on. All right. So let us look at equivalence and equality of sets. So two sets A and B are equal if A is a subset of B and B is also a subset of A. That is, all the elements of set A are the same as elements of set B. Okay, for example, if you have a set A contains if a set A is 1, 2, 3, and 4, and you have a set B, irrespective of the order of arrangement, maybe 2, 1, 4, 3. All right, so this is 2, this is 2 here, this is 1, 1, 2, 3, 4, this is 1, 2, 3, 4. All right, so we can say a set A is equal to a set B. Okay, now, but let's look at the equivalence of sets. Most people get confused in all this, but the way we can look at it is that, okay, 2 oranges and 2 mangoes are equivalent. 2 oranges, all right, and this is a sign of equivalence, and 2 mangoes, all right, are equivalent. We also can say that 5 cups of rice and 5 cups of beans are equivalent in quantity, right? If you have like 5 cups of beans, right, it's equal to 5 cups, of rice. So they are equivalent in quantity. They are equivalent in quantity. Okay. All right. So if a set also have equal numbers of elements, we can also say that they are equivalent. For example, if you have a set A is equal to A, B, C, D, E, all right, and we have a set C is equal to 1, 2, 3, 4, 5. All right, so you see that all the elements here, they are 5, 1, 2, 3, 4, 5, and all the elements of C are 1, 2, 3, 4, 5. So we can say that A is also equivalent to C. Okay, so we can also say that like a 10 textbook is equivalent to a 10 exercise books. All right, Okay, let's move on.
All right, so we look at a null set or empty set. Now, take for example where there is nobody in the classroom, probably during holidays or after school hours. So we say that the classroom is empty of persons at that time. That means there is nobody in the classroom. So we refer to it as an empty or null set. So a null set is a set that contains no elements, no members. So and it is denoted this. It is denoted this. All right. All right. That's a null set, or we'll write something like this. That's a null set. So you note that uh, the enclosed brackets, there is nothing inside there, right? That's a null set. Okay, so if we have something like this, let's say we have something like this and we have a dot here, all right, or we have something like this and we have this. So this particular one is not an empty set. All right, it's not an empty set because it contains a dot, all right, which is an element. This one also is an element, so it contains that. So, but when there is no element inside a set, we call it a null set or empty set. All right, let's say take this example when we have a set A, uh, human beings with tails. All right, so we said this particular one, is an empty set because you can never have human beings with tails. All right, so a universal set contains all possible elements under consideration, and it is denoted by this. So you can have, this particular sign, or he. All right, is used to denote a universal set. All right, so if we are discussing medical students or at a University of Ibadan, take for example, the university students, okay, we say they are medical students, so the whole students of the University of Ibadan can be our universal set, right? So the whole um, student of the University of Ibadan can be our universal set. That means it's a fixed or global set, a fixed set. The whole student in the University of Ibadan can be our universal set. So the universal set varies as our group of reference varies. So they varies. And then, like I said, you can denote your universal set with this or this. All right. Okay, so let's look at a unit set. So a unit set is a set that contains only one element. All right, that's a unit set. For example, this particular set A contains only X. So it's a unit set because it contains that one element X. All right, so let's look at complementary sets. Okay, look at complementary sets. So if you are given that A is a subset of the universal set. Take for example, um, universal set of students in the University of Ibadan. So A could be a student in geography department. So A is a subset of the universal set. So the elements of the universal set which are not in set A constitute a set which is called complement of A. Okay, so now take for example, we have a universal set. It's talking about all integers. All right, said all integers. All right, so we have a universal set of all integers, and we say that A is all odd integers. All right. If A is all odd integers, so it means the rest that is remaining. So we say A complement. A complement means all integers that are not odd numbers, odd integers. All integers that are not odd. That is A complement. So A would then be all the even integers. All right, that is the complement. All right, take for example, we have this one also. We're given a universal set of a number from 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. All right, so if you're given a universal set of that, and we're saying that we're given that A is contain element 2 and 4. All right, so A complement will be any other thing that are not 2 and 4 in the universal set. So if my A complement will be, I'll take 2 out, I'll take 4 out. So my universal set, A complement, my A complement will be 1, 3, okay, 5, 6, 7, 8, 9, and 10. All right, so that is a complement. So what we are saying is that if A is a subset of a universal set, if a given set is a subset of a universal set, then the elements of the universal set which are not in set A, right, constitute a set which is called a complement. All right, so let's look at cardinality of a set. So if a set B is given as this, right? It's given like this. It says A, we have G, B, E, and C. So these are 5 elements in the set. So 1, 2, 3, 4, 5. We have 5 elements in the set. So the number of the elements in the set is called its cardinality. All right. So since the set B has 5 elements, the cardinality is 5. All right. So you set B. All right. So set B will be what? All right, and B. Okay, which is 5. So the cardinality is the number of elements in the set. So if you are given another set C to be say Q, P, R, G, Z, and O. All right, so if you were to look at the cardinality of a set C, say 1, okay, 2, 3, 4, 5, 6. All right, so the cardinality of set C, all right, is 6. So that is how cardinality is. All right, so let's look at intersection of sets. The intersection of two sets A and B is a set which contains all the elements that are in A as well as the elements that are in B. All right, so I will denote that as A. We denote it as this particular this is an intersect sign, this particular one. So A intersect B is written as this. All right, so now let's take an example. For example, in a school, let's say in a school we have the principal wants to find out the number of students offering both mathematics and physics, maybe in an SS3. So if we are given that M is the student of mathematics, right? Just short form like that, and we're giving P student of physics. Okay, all right. So we're giving C to be student offering students offering both mathematics and physics. All right, so if you're given such, Now, what do we do? Let us have a short Venn diagram for that. All right, so we're given like this. All right, then do like this. So this is M, number of students offering mathematics. P, number of students offering physics. So this particular middle is an intersect. Is an intersect. Okay, all right. So this particular point is an intersect. It's intersect. All right, which shows the of people, number of people, number of students offering both mathematics and physics. So this particular one is the um, intersect. All right. So if you look at the other example here, we have these particular numbers are given unto us. I mean, we have R 2, 4, 6, 8, 10, 12, 14, 16, 18, and we have Q to be 1, 2, 4, 6. So R intersect Q will be the element that both R and Q has in common. All right. So what are the elements that both has in common? Okay. You can see they have 2 in common. This is 2. This is 2. All right, that's why we pick 2 here. They have 4 in common. Okay, they have 4 in common. They also have 10 in common. Okay, 10 is there. Do they have 20? Yes, they have 20 in common. All right, so what the element they have in common are 2, 4, 10, and 20. So R intersect Q will be uh, 2, 4, 10, and 20. All right, so looking at union of sets, a practical example can be found in a school where the student of one class are combined with student of another class whenever a teacher is absent. Or probably in a market, you have different articles which they are combined together. You can see somebody selling set of shoes, with a set of dresses, set of jewelries, they can be selling all those things together. So the simple combination of sets is called the union of sets. All right, so if we have this example, we have A, let me give an example. A is have an element of 2, 3, 5, 7, and 11. And I have B, okay, it's also giving me 1, 3, 5, 7, and 9. All right, so how do we form, let's not forget A union B. Union is denoted like this symbol. All right, so this is union, right? Union of set is this. All right, this is union. The intersect is this. This union. All right, intersect is this. This is an intersect. All right, so we have A union B is going to give us all the elements. When you have your union, all the elements that are contained in A and all the elements that are contained in B are captured. Okay, so I'm going to start with this. I have 1 here. I'm going to pick 1. Okay, I have 2 and there is no 2 here. I'm going to pick it. I have 3, both 3 here, so I'm going to pick one of them. That's 3. All right, I have 5 here. Okay, 2, 5. I'm going to pick only 1 5. Okay, I have 7. Okay, so I'm going to pick 1 7. Okay, I don't have 9 in both, so I'll pick 9. I have 11. I don't have in both, I'll pick 11. All right, so if you check this, you will see that for set A, 2, 3, 5, 7, 11 is going to be captured here. 2, 3, 5, 7, and 11. And for set B, 1, 3, 5, 7, 9. 1, 3, 5, 7, 9 is also captured. So when we have a set that's A union B, all the elements of the two sets are captured in the union, right? It's as if a man and a woman gets married. So all their properties are just together. So if you already have a fan, I may not be bothered to, have two. Okay, so let me say that again. Probably you have a man and a woman trying to get married. So the man A, has so many things like a fan, maybe HP fan. You have thermocool. Okay, you have a thermocool freezer. Okay, you have LGO television. All right. Okay, so you have 15 inches. You have maybe size 240. All right, so you have fan, maybe 15 inches fan. All right, so and you have the woman also has similar things as HP fan, same thing, 15 inches. All right, so but he has um, uh, uh, um, maybe stove. Okay, the woman have a stove, a cooking stove. All right, so this is what the woman has. This woman, okay, has maybe also LG television. Okay, the same thing, 15 inches. All right, so and they are trying to form a union. They are coming together as husband and wife. So now they both have HP fan. So probably they want to just discard one of them. So they just want to say, okay, we have the same fan and we are just going to have one room. So let's just take, that fan alone. Okay, you can give the rest. So, but the woman has a stove, the husband doesn't have. So they pick the stove, cooking stove. All right. Okay, so both of the man has a freezer, the woman doesn't have. So yes, so we need the size 240 thermocool freezer. All right. So, but they both also have 15-inch LG television, and because they only have one sitting room, just want to keep one, so they can now have LG television. All right. So that is the union. That's the union that we're talking about. Okay, so let's look at this one quickly. Union of sets. I have HEAP here, and this one is a L, LAKE. All right, so let's look at it. So G union H will be, I think I have H here. H is there. All right, so there is no E here. Okay, E is easier, so I take one. What about A? A is here. I pick one. P, okay. All right, I stop. All right, so pick P. L is not in G, so I pick L. Okay. Then A, I've already picked A. K, or I've not picked K, so I pick K. Then he is already taken. All right, so if you look at it, you will see that elements of G are contained in the union HEAP, HEAP. Then LAKE, LAKE is also contained, and that is how the union of set is. All right, so let's look at the disjoint of set. So disjoint set is set A and B are said to be uh, disjoint if they have no common elements. So if they have no common elements, we said they are disjoint. For example, if I have a set, say a set A is equal to say 1, 3, 5, 7, 1, 3, 5, 7, and I have a set B is equal to say 2, 4, 6, 8, 10. All right. So you see that 1, 3, 5, 7 are the elements of A. All right. And you can never see 1, 3, 5, 7 here. All right. So we say that A and B are disjoint. Okay. A and B are disjoint. They are disjoint sets. All right. Why? Because the element of A is not the same as the elements of B. The members of A, they are not the same as the members of B. So what we say at that point is that, when we have an intersection, then we have similar things. All right, so when we say this element A is element B, so what we are saying is that there is nothing here. So when we have 5, 7, 8 here, and I have 1, 2, 3 here. All right, so this is a disjoint set because there is nothing, here. So when we say that, we'll say A intersect B is what? Is empty, is a null set, all this. All right, so that is what we call disjoint set. All right, so let us look at the power of set. Let's look at the power of set, and when we talk about the uh, power of set, we'll look at the subset of a given. We look at the subset of a given set. For example, if set A is finite, don't forget I talked about finite before. Those are the definite um, uh, sets. All right, so now if you find out with an element that is we have A to be 1, 2, 3, 4 to n. So the power of set of A is 2 raised to power A. All right, so what we are saying is that if we have a set A, okay, all right, and it has you are given like maybe 1, 2, 3, and 4. The elements, the cardinality or the number of elements here is actually 5, is actually 4. That's the cardinality. Don't forget that we have this as cardinality. So my power of set is going to be 2 raised to power n. And n here is 4, so 2 raised to power 4. So the possible outcome that you're going to have here is 2 times 2 times 2 times 2, and that is 16. So you're going to have the possible outcome of 16. Okay, so if we have 3, like what we're given here, so if we only have 3 here, okay, only have 3 there. So the cardinality is 3, okay, right? We have this is an element, second 3, and third element. So we have 3. So then we have our power of set. That's our power set will be 2 raised to power n. So here is going to be 2 raised to power 3, which is 8 possible outcomes. So that means you can have the subject can be formed from set A here, with 3 elements. It's going to be sometimes that can be anything, there may not be anything here. So a null set is also part of it. So you have a null set, that's 1. We have 1, 2, 3. We can have 1, 2, 3. We can have 1 alone. We can have 2 alone, 3 alone. We can have combination of 1, 2 as the number of subset that we can get from this. Then 1, 3, okay, could be a subset. 2, 3 can also be a subset. Then if this place is empty, this empty or null is also a subset of this particular set, which has 3 elements. Okay, let's look at laws of algebra. We have commutative law, and this commutative law we have whenever we have A intersect B is also the same thing as B intersect A. And if you have A union B is also equal to B union A. All right, so that's certain. That's what we call the commutative. We have commutative law. Also, we have associative law, which says when we have A intersect, right, B intersect C. All right, it's also the same thing as A intersect B and also intersect C. All right, don't forget we have intersect here, we have intersect here also. So when we have A union right? And we have B union C, right? Don't forget they are different sets. A is different from B, B is different from C. So the union also is going to give us A union B, right? Everything union C. All right, so we have distributive law. Our distributive law says that A intersect B union C is equal to A intersect B, then you put this union, then A intersect C. That's distributive law. The same thing goes with A union B, then B intersect C. Don't forget that what we have here, we have intersect here, we have union in the brackets. So here we just have union here, right? So inside, for this particular one also we're going to have the intersect. So we have law of absorption, and we'll talk about law of absorption. We're looking at whenever we have A intersects A union B. For example, we have A intersects then A union B. So what does the law of absorption say? What we're saying that the law of absorption says that everything here is A. All right. Okay. A intersects A union B. Then when we have A union, right? A intersects B is also A. For example, you are given A is equal to uh, 1, 2, 3. Okay, you are given B as okay, let's say 2, 3, 4. All right. So if we look at this now, let's do A intersect B. All right. So this A intersect B will be given. This one is common. This is common. 3 is common. 3 is common. So 23. So A intersect B is actually 2 and 3. That's A intersect B, 2 and 3. All right, so we now want to do A union A intersect B. All right, so this is A now. A is 1, 2, 3, right? And we have B. We have A intersect B. So we want to do union of this 2, 3. All right, this intersects. This is the A. All right, so let's do the union of this. All right, so when we want to do this, we do our union will be 1. Okay, 1 is there. Pick 1. Then 2 is common, 2. Then 3 is here, 3 is here, pick 3. All right. All right, so you discover that this particular one is also A, which is this particular one. So that's what we have done here. So A union A intersect B is A. Also A intersect A union B is also A. That is the law of set absorption. All right, so let's look at idempotent laws. So which means what it means is that when we have A intersect A, all right, is A, that's given. A union A is A, all right, that's given. All right, so if we have the De Morgan's rule, De Morgan's rule state that if we have A intersect B complement, so what we're going to have is A complement union B complement. It's the same thing. Equally, if you have A union B, all complements, we're going to have A complement intersect B complement. We'll be showing several examples as time goes on. All right, so let us look at difference of sets. All right, so the difference of two sets A and B denoted A minus B is the set of all elements in A which are not in B. For example, before the example, A minus B can never be B minus A. So let's take, for example, if we have a set A to be 1, 2, 3, 4, 5, 4, 6, and 8, we have B to be 2, 1, 3, 5, 7. So, okay, I want to do A minus B. All right, in A, I have 1, 2, 3, 4, 6, 8. All right, so I want to do the subtraction. All right, so I want to do A minus B. So what I need to do is I've written the set A. This is set A that we're given, and I want to subtract B. All right, so I have 2 here. Okay, I have 2 here. All right, I'll take away 2 here. I have 1 here. I'll take away 1. Okay, I have 3 here. I'll take away 3. What about 5? Okay, I don't have 5. Yeah, so I can't take away 5. 7, I can't take away 7. So A minus B is going to be element 4, 6, 8 that is remaining. All right, so um, let's look at B minus A now. So this is B minus A. All right, these are my B. So let me just quickly write okay. All right, so look at small user I can use. All right, to get that one done. Okay, I want to do B minus A, so let me just write my B. My B is 1, 2, 1, 3, 5, 7. Okay, that's my B. All right, I want to take away A. I want to take away my A. So I have 1 here. Okay, I can take away 1. I have 2 here. I can take away 2. I have 3 here. I can take away 3. I have 4 here. I can take away 4. 6. I can take away 6. 8. I can take away 5, 7. So my B minus A is 5, 7 here. All right. So you see that B minus A is not equal to A minus B. All right. So in this first part of the video, I will just want us to look at other laws of sets. Okay. So other laws of sets will be looking at laws of complementation. Law of complementation says that A intersect A complement is a null set. What does that one mean? If we have A, all right, if A is 1, 2, 3, 4, 6. Okay, so A complement, that means things that are not present in A, this is actually a null set, right? Because just A. So if you are not saying that A, this one is intersecting a null set, no. So this is actually a null set. So A intersect A complement is a null set. So A union A complement is a universal set. Right. So if you have a universal set, okay, of all integers 1, 2, 3, 4, 5, 7, and this is your A. All right. So A complement here will be other things that are not here, which is the things that are in the universal set. All right. So whenever you now have A, this particular one, A union A complement. So you write everything here, and things that are in A complement that are not A, that are outside A, then definitely you're going to have everything in universal sets. We have A union A complement is universal set. Universal set complement is a null set. Null set complement is a universal set. Then the additional properties we have a null set intersect A is a null set. Null set union of A is A. Universal set intersect A is A. Universal set union A is universal set. So let us look at laws of inclusion. Right. So the laws of inclusion says that if A is a subset of B, if A is a subset of B, A is a subset of B, and then B is also a subset of C, then A is a subset of C. All right. So that means if A is a child of B, okay, this is a Taiwo. There's a Taiwo is a child of Bola. All right. And Bola also, which is B, um, is a child of Collins. Collins, okay. So say Taiwo is a child of Bola, and Bola is a child of Collins. So we can also say that Tolu, which is A here, is a subset as a child of Collins. All right. So if A is a subset of B and B is a subset of C, so we can say that A is a subset of C. All right. And another one is if A is a subset of B, if A is a subset of B and A is a subset of C, A is a subset of B and A is a subset of C, then that means A is a subset of B intersect C. Alright, A is a subset of B intersect C. So if A is a subset of B, then A is a subset of B union C. Alright, for any set C. So that's what we're saying for any set C. We'll say if set is a subset of B, then A is a subset of B union C. Same way. If we have A subset of B and we have this also, we have A is a subset of B union C for any set C. All right, so we're going to stop here in the first part, and in part 2 of this video series, we'll be looking at applications of Venn diagrams. We're looking at application of Venn diagrams, how you can apply um, set to solve real live problems using Venn diagrams. I want you to subscribe to this video, and we'll be looking forward to hear from you if there are questions. So please subscribe. Thank you very much. So I will see you in the next video. That's the part 2 of this set. All right. Thank you. Bye.